our next speaker. So this is Daniela from Heidelberg University. Daniela was actually the winner of the poster competition last year, and the talk title is "What Does Breath Methane Tell Us?" Daniela can't join for live questions, so please do put the questions in the Q&A as we go through the recorded presentation. We'll make sure Daniela gets a copy of those and answers back to anyone that has questions. I think what's particularly interesting about this, we heard earlier about devices such as OMED for measuring hydrogen methane. Rick talked about how methane measurement is being used day in, day out in GI type conditions. So I think Daniela's presentation here is really exciting about looking beyond conventional GI applications for gases such as methane. Thanks, and over to you, Daniela.
Welcome to my talk. My name is Daniela Polag, and I'm working at Heidelberg University in the research group of biogeochemistry led by Professor Frank Kepler. I will present our work of over 10 years and what we've learned about human breath methane during this time. So as you all know, human breath contains over 3,500 volatile organic compounds. The challenge is not only to interpret endogenous VOC production in terms of useful biomarkers, but to overcome the current limitation by standardized methods. First, endogenous VOCs needs to be clearly distinguished from background VOCs. This is where the advantage of methane comes into play. It is the simplest of the alkanes and can be easily measured by GC with an accuracy of a few ppbV due to its naturally high abundance of 2 ppmV in ambient air. I've listed some facts that were state-of-the-art 10 years ago when we started our research. Methane has been known as a component of human exhaled air for about 50 years. It is generally said that a quarter of people emit breath methane, which is different from background levels. And what we still read in many publications today, breath methane is associated exclusively with anaerobic microbial activity in the gastrointestinal tract and is thought to be primarily related to intestinal motility. There are also numerous medical studies attempting to link increased breath methane production with gastrointestinal diseases, including serious diseases such as colon cancer. So how did we get into the game of breath methane? As an Institute for Geosciences, medical research is not exactly our specialty, to be honest. So it all started by chance at an open day at our institute where we wanted to present our analytical skills by GC. To illustrate this, the participants' breath methane was measured to determine their personal climate footprint. In our own interest, age and gender were also recorded this day. When we analyzed the data, our scientific curiosity was piqued, and we collaborated with the gastroenterology practice to investigate other parameters such as gastroenterological diseases that could have an impact on methane emission status. Our main question was, is there a factor which mainly influences the status of breath methane emission? Do people who differ significantly from the background methane emission have something in common? As a major result, we found that age has a significant influence on the status of breath methane emission. When an age interval of 15 years is selected, correlation analysis shows that there is an approximately linear relationship between the percentage of breath methane producers and age group throughout lifetime. Interestingly, when the age interval is reduced to 5 years, correlation analysis now shows that the relationship between the percentage of breath methane producers and age is much weaker. However, considerably more important, this dataset now reveals that there is a drop in the percentage of breath methane producers in 3 consecutive age groups, in the age range between 50 and 65 years, when compared to the previous age groups. What this sharp drop causes is rather questionable, but it is noticeable that it is placed in the age group of hormonal change, at least for women. Another result shows the relationship between age and sex. I always ask the students in the lecture whether they think that men or women are the bigger climate sinners. The answer is, it depends on age. In the graph here, the ratio of female to male breath methane producers plotted against age in intervals of 15 years. In ages ranging between 20 and 50 years, female producers outnumber male producer with a general decreasing trend. Interestingly, the observed dominance in female producers in ages ranging between 10 and 50 years coincides with the phase of female fertility. From the fifth decade, the ratio reverses in favor of male breath methane producers, with a increasing dominance of male breath methane producers with increasing age groups. So, which factors mainly influence the status of breath methane emission? The answer is age. However, the reason for the general increase in the percentage of breath methane producers with age is unclear. It is probably caused by a number of different factors, of which the elderly are more likely to have predisposing conditions. For example, factors such as carbohydrate malabsorption, decreased gut motility, increase of gastrointestinal diseases, and hormonal and immunological changes might become more prevalent during the aging process. The next question we were interested in was how many people produce methane and in what quantities. So most publications state that about 1/3 or 1/4 of humans are considered methane producers, depending on the colonization of the gut with methanogenic archaea, based on the classification terminology of high and low emitters. To test these assumptions, we used laser absorption spectroscopy to precisely measure the concentration and stable carbon isotope signatures of exhaled methane in breath samples from over 100 volunteers. The exhaled methane values of all test subjects were significantly higher than the background values for inhaled air. Thus, in the following, we divide the groups into low, medium, and high emitter. So are only 25 to 30% of the people breath methane producers? The answer is, it depends on the limit values set and on analytical precision. This is the first time that analytical evidence is available that clearly shows that all the tested persons exhale methane in varying concentrations, which were always higher than the amount inhaled. In addition, stable carbon isotope studies, which are not shown here, unambiguously confirmed that this additional methane was produced endogenously in the human body. So far, little attention has been paid to the temporal variability of breath methane production in the individuals. We have therefore carried out a number of longitudinal studies on various individuals who, on average, showed medium to high methane emissions. Here is an example of the breath methane variability of a high emitter over a period of almost 4 years. Breath methane values fluctuate in a wide range, from almost 0 to about 60 ppmv. The gray areas refer to periods of physical discomfort associated with various infections, inflammations, and immune system disorders caused by vaccinations. Interestingly, there appears to be a slight correlation between the periods of physical discomfort and a reduction in methane production levels. In contrast, here we see the long-term monitoring results of another methane emitter, which is more in the range of medium methane production. It has been shown that an attack of multiple sclerosis leads to a greatly increased breath methane levels. Specific medical treatments, such as a chelate treatment and an alpha-lipoic acid treatment, also appear to have a similar effect on breath methane. To quantify the actual health status, a subject evaluated subjectively his physical condition on a numerical basis prior to breath methane measurements. So 1 represents good health conditions, whereas 5 indicates bad health conditions. The subjective well-being of the subject seems to be clearly correlated to methane production. Thus, allergic complaints and a gastritis occurring during the measurement period and associated with bad physical condition is accompanied by a higher breath methane production. So, how does breath methane fluctuate over time? The answer is to a very large extent. As a major outcome, breath methane shows considerable variability within a person-specific range of values. So long-term monitoring of breath methane production in individuals reveal a high dynamic range. Breath methane production status occasionally change from medium-high emissions to low emissions and vice versa, which could often be related to health status or physical condition change. These results indicate that breath methane is a potential biomarker not only for gastrointestinal diseases, but also for general inflammatory processes and immune reactions. Based on these results, we studied the factors that influences breath methane in more detail. To evaluate the effects on breath methane through oxidative reductive stress reactions, 2 subjects were monitored over a period of almost 2 years. So here are the results of the first volunteer. During the study period, various immune reactions occurred that were triggered by infections, inflammations, and induced perturbations by vaccination. The latter in the graphic here, they indicate the specific physical events such as allergic rhinitis, infections, COVID-19 vaccinations, and also physical complaints such as headaches or muscle aches. For better characterization, breath methane values were empirically divided into 3 categories, delineated by percentiles expressed by different colors. Thus, the red color indicates the 33% level referred to as activated immune level. Yellow, the 66% level referred to as medium level, and green, the remaining data referred to a normal level. It can be seen that during periods of immune inflammation events, breath methane values of the subject generally shows an increase by a factor of 25 compared to normal values. Especially after vaccination, very large breath methane shifts occurred. In the zoomed area here, we see the results of the first COVID-19 vaccination, which shows a breath methane maximum 3 days after vaccination. A completely different pattern can be recognized for the second volunteer. In contrast, breath methane values showed a general drop during immune inflammation events with a factor of up to 3 compared to normal level, which can be seen here for the vaccination or here for COVID-19 infection. Again, vaccination has a strong effect on breath methane. In contrast to volunteer A, volunteer B exhibited a sudden decrease in breath methane within the first few hours after vaccination. Minimum breath methane levels could be observed 1 day after vaccination. Thus, breath methane values almost decreased by a factor of 10 relative to the normal level. After 4 to 7 days, breath methane values return to medium level again. The potential mechanisms of the observed methane production and degradation might include microbial as well as non-microbial pathways, which are illustrated here. Non-microbial pathways that occur in eukaryotic cells under aerobic conditions were recently described. Those mechanisms are based on reactive oxygen species generated by oxidative stress and the interaction with iron and methyl donors. So in principle, it is also possible that infections and inflammations by vaccination might have an effect on methanogenic population. Growth and/or activity of methanogens could be either stimulated by a greater availability of potential precursor substrates or by the inhibition of alternative pathways. Can breath methane serve as a bioindicator for immune reactions? The answer is yes. So summarizing the results of methane breath monitoring over 2 years in 2 contrasting subjects, we observed that an activated immune level was almost always indicated by exceeding individual breath methane limits. Long-term monitoring studies of breath methane from several volunteers provided evidence that abrupt deviations in breath methane levels from the baseline were linked to inflammatory processes and immune reactions. The observed individual breath methane dynamics supports the hypothesis that methane has a potential bioactive role in immunology and might serve as a marker of oxidoreactive stress. So in a follow-up study, we focused on non-microbial methane production with the question, is there another source of methane in the body besides archaea? To answer the questions, a volunteer applied isotopically labeled methylated sulfur compounds such as dimethyl sulfoxide and methionine orally, to blood samples, and on the skin. DMSO and methionine were used here because they are considered potential precursors of the non-microbial methane production observed in plants. So DMSO has the ability to rapidly penetrate through the body and is known as a free radical scavenger. Here we see the isotopic excess in breath methane after the oral intake of hydrogen and carbon-labeled DMSO. Both isotope tracers, hydrogen and carbon, evidently indicated partial conversion of the methyl group of DMSO to methane by processes within the human body. So similar results were obtained from the blood samples and the skin experiments. The observed formation of methane from the sulfur-bonded methyl groups of DMSO or methionine provides strong support for a radical-driven process of methane formation. Based on the 3 applied isotope labeling experiments and a previous study demonstrating ROS-driven methane formation from in vitro experiments of many organisms, we propose a reaction scheme here showing the interplay of methyl precursors produced via metabolism or externally supplemented ROS and iron species that eventually leads to the formation of methane in humans. So, is there another source of methane production in the body besides archaea? The answer is with high probability yes. We are aware that the investigation of ROS-driven cellular methane formation is only one subject is too low of a sample size to draw broad and general conclusions. However, this study represents the first proof of concept that cellular methane formation occurs in the human body and is most likely a result of the interplay between ROS and methylated substrates. This process can currently only be made clearly visible by applying stable isotope tracing techniques to distinguish methane formation in humans from that of microbes living in the gastrointestinal tract. So here's a summary of our most important breath methane research findings from the last 10 years as a take-home message. So all these findings have now been published in peer-reviewed journals. So we have learned that age is the main factor for methane emitter status. Almost all people produce at least small amounts of breath methane. Breath methane is highly dynamic, and cellular oxidoreductive stress plays a major role in breath methane production. And methane is a bioindicator for general immune responses associated with increased methane production or methane degradation. So, with the knowledge we have gained over the last 10 years, we can now review the statements from the beginning that can still be found in many publications today. So, the statement that 25 to 30% of people are methane producers is too general because we found that breath methane in an individual is highly variable over time. We also found that microbial activity is not the only source of methane formation in the human body. Rather, it is likely that ROS-driven methane formation may be a necessary phenomenon of aerobic life. Consequently, non-microbial aerobic methane formation should be highly variable in time and source strength, as it may be an integral part of the cellular responses toward changes in oxidative status present in humans. Also, the observation that breath methane levels increase with advanced age might be an indication of the human age-related increase in systemic inflammation accompanied by enhanced ROS levels. Generally, particular caution is required in cross-sectional studies. The age relationship of breath methane production becomes a crucial factor when interpreting the results of correlation studies which investigate the relation between breath methane production and specific diseases such as diverticulosis or large bowel cancer. However, the high variability of individual breath methane levels fundamentally calls into question the usefulness of measuring individual values. Although our study cannot clarify whether the observed methane dynamics following immune reactions are solely driven by the generation of ROS or controlled by microbes or a combination of both, it highlights methane as an in vivo parameter that might, for example, provide substantial benefits in classifying the efficacy of treatments such as vaccination or during the application of personalized medicine. Therefore, in future studies, additional immune parameters such as antibody level can be recorded to calibrate breath methane values according to the quality and extent of the immune response. Future studies should focus on deciphering the potential physiological role and predictive regulation mechanisms of methane in humans. However, further investigations are required to obtain clear evidence of potential dysbiosis or non-microbial methane production in humans and the underlying processes of its formation and degradation. So that was our story about methane breath research. I end this talk with a photo of our working group doing breath methane research on top of the Zugspitze. Thank you for listening, and many thanks to the staff of Ulster Medical for the opportunity to present my findings to this community. I hope you enjoyed the presentation. If you have any questions, comments, ideas, or possible study projects, please feel free to contact me. Thanks.
So as a quick reminder, any questions for Daniela, please do post them into the Q&A. We'll make sure they get to her and she will respond, and we'll post those responses for everyone attending the conference. I do find that truly fascinating. There's not very many instances where you have longitudinal monitoring over quite long periods of time. And obviously one of the limitations is the sample collection or having to go into the lab to do it. We're already seeing with the OMED device where you can distribute a large number of devices to individuals in the home and collect longitudinal data sets. Some really fascinating results coming through from that as well. So if there's anyone interested in research applications related to methane building and what Daniela has talked about, do reach out to us and we'll happily discuss that a bit further.